Hope you have seen the last two lectures. If not, please do it before you watch this lecture. In the last two lectures, we have seen the notion of correctness of a DFA design and the principle of mathematical induction, which can be used to prove the correctness of a DFA design. And the objective of this class is to use the principle of mathematical induction to prove the correctness of a DFA design. Okay, so how will you prove the correctness of a DFA design? If you recall, there are two parts for a correctness proof, and they are proving the soundness and completeness of a DFA design. If a DFA design is both sound and complete, then it is said to be correct. Okay, now we are going to use principle of mathematical induction to prove the soundness of a DFA design. So, given an example DFA like this is the one for odd number of A's. Then what is soundness? If you recall, soundness is this. If X is a string in the language of the automaton, then X contains odd number of A's. Or in other words, in soundness, we are trying to prove that the DFA will not accept a bad string. In this example, a string is bad if there are even number of A's. Okay, so we want to prove that when X is accepted by the DFA, then there are odd number of A's in X. Okay, this is what we have to prove. And to prove it, we will be proving a subclaim first. And what is the subclaim? Which is a predicate on a natural number, P of n. And what is this predicate? Let X be a string of length n. Then if the computation of X in A ends in state O, then number of A's in X is odd. And if the computation of X ends in the state E, then the number of A's in X is even. So basically we are claiming that given a string X of length n, the processing of the input X ended in the state O, then the number of A's is odd. And if the processing of X ended in the state E, then the number of A's in X is even. And that is the claim. Let us try to use the principle of mathematical induction to prove this claim. Please don't confuse the last statement, which basically tells that if the processing of the input ends in the state O, then there are odd number of A's in the input string. And if it terminates in state E, then there are even number of A's in the input string. Okay, to use the principle of mathematical induction, we just need to prove that the predicate P satisfies condition 1 and 2 of mathematical induction. What is the condition 1? Which is the induction base, which tells that the predicate is true for n is equal to 0. N is equal to 0 means the length of the input string X is 0. That means the input string is the empty string epsilon. Okay, when length is 0, what is the string? It is the empty string. Since input is the empty string, we have not processed any simple, and hence where are you in the automaton? You are in the state E only, because you have not processed anything. So in that case you finished in E. And here we are done because the number of A's in X when X is empty string is 0, because in empty string no A's are there, it is 0, and which is an even number. So we established that for the base case we finished in the state E, and there the number of A's is even number. So we proved the base case. And now induction step, there are 4 cases. And what is the induction step? Case 1. Case 1 is that assume that the statement is true for K. Okay, that means when the length of x is k, it is true. And take the input x concatenated with a. Okay, assume that the statement or claim or predicate is true when the length of x is k for all strings of length less than or equal to k. Take the, and we have to prove it for k plus 1. That is, we have to prove it for a string of length k plus 1. So how will you get a string of length k plus 1 from x when the length of x is k? You append a symbol to it. Suppose you, first case is when you have a as the next symbol. Okay, and there are two cases now. One is the processing of xa ending in o, and that is the case 1. The processing of xa ending in o. Okay, then what you can say? And if you recall, this is representing that the processing of xa from the state E is the start state is equal to O, mean the processing of xa is ending in O. Okay, so processing of xa ending in O means the last A was coming from here. Okay, reading from here. You were in this state to read the last A, and that is why when you finish reading xa, you are into O, means when you finished reading x, you were in E, and that is what it is given. This is by the given DFA definition. That means the processing of x ended in E, and that is why from E, when you processed A, you came into O, and that is why when you processed XA, you ended in O, means when you processed X, you ended in E. This is from the definition of the DFA. Okay, this means the processing of x ended in E. Then the induction hypothesis, from the assumption we know that the number of x, number of a's in x is even from the induction hypothesis. Okay, if the number of a's in x is even, then what will be the number of a's in xa? An even number plus 1, which is an odd number. Okay, so basically we proved that if the processing of xa ends in the state O, then there are odd number of a's. So that case is done. Then the second case where you are going to read xa, and when xa stops in E, what happens? Basically we want to prove that then the number of a's in xa is even. That is what we have to prove. So this can be written as the processing of xa ended in the state E. Okay, so from the machine, what you can say, where the processing of x would have ended, it must have ended in O, because if it ended in O, then the next A is taking you to E, and that is the case. Okay, this is from the definition of the DFA. Okay, then from the induction hypothesis, if the processing of x, which is of length less than or equal to k, is ended in O, the hypothesis tells you that the number of a's in x is odd. Then what is the number of a's in xa? An odd number plus 1 is an even number. Okay, then you are done, because you proved that when the processing of xa ended in E, the number of a's in xa is even. So that case is also done. Now the remaining two cases, when you get a string of length k plus 1 by taking b as the last symbol, that is the next case. Okay, the input symbol is b, next is b, so xb is the input symbol, x is a string of length k. Okay, suppose the processing of xb ended in O, you can write it as the processing of xb ended in O. Then from the definition of the DFA, you know that the processing of x and x also ended in O. Why? Because from O, for a B you are taking a self loop. So the previous state was also O. That's why it's O. If it is O, that means the processing of x ended in O. Then from the induction hypothesis, we know that the number of a's in x is odd. Okay, then after x, what you are processing? It's a b. Then what will be the number of a's in xb? An odd number plus 0, because you are not processing a, plus 0, which is an odd number. So basically what you proved is that when the processing of xb ends in O, then there are odd number of A's. So you did that also. Then the last case is case 4, where the processing of X be entered in the state E. This is how you write it. Okay, then from the definition of the machine you have the processing of X also entered in E. Then from the induction hypothesis you have the number of A's in X is even. Then what will be the number of A's in XB? It's even itself, because an even number plus 0. Then you have done. Okay, so you have done all the 4 different cases in the induction step, and hence you proved that this subclaim is true. Then you can use that subclaim to prove the soundness of a DFA design. Claim is that if X is an element of the language accepted by A, then X contains odd number of A's. How will you prove? Suppose that X is accepted by the DFA. Okay, that means X is entered in the state O. You accept means you entered in O. Okay, then subclaim is telling you that the number of A's in X is odd, and so you are done. So that is sound. Soundness means if the DFA is accepting something, then the input, whatever is accepted, is in the language that you need. Okay, and now the second one, which is completeness. What is completeness? If you recall, completeness means if X is a string with odd number of A's, then you have to prove that X is in the language. Okay, so how will you prove? Again, we are going to use a subclaim. What is a subclaim here? It's a predicate on n. And what is the predicate? Let X be a string of length n. And the predicate is if the number of A's in X is even, then the processing will terminate in E. And if the number of A's in X is odd, the processing of X will terminate in O. That is the claim. Okay, subclaim is telling that if you process a string X with odd number of A's, you will end up in O. And if the number of A's in X is even, you will end up in E. This is the reverse claim. You may go back and see what we did for soundness. Okay, anyway, this is the claim. And now you go for the base case. What is the base case? You have to prove it for n equal to 0. N equal to 0 means length is 0 and the string is empty string. So you have number of A's in the empty string is 0, an even number. So it remains us to prove that the processing of epsilon is ended in the state E, and that is true because you are not processing any simple, so you are ending in E itself. So that is done. Okay. Now you prove the 4 steps in the induction step. The first is that you assume that it is true when the length of X is less than or equal to K. Okay, the case 1 is you are getting a length K plus 1 string which is XA. Okay, and suppose assume that XA contains odd number of, and assume that X contains odd number of A's. If X contains odd number of A's, then from the induction hypothesis you know that the processing of X ended in O. Okay, if X contains odd number of A's, then from induction hypothesis the processing of X ended in O. Okay, so you are in O when you processed X. Then what is the next simple? A. Where will you go? You will go to E. So the processing of X A ended in E. Okay, now it is proved. Why? Because you ended in E. And what is the number of A's in XA? Number of A's in X was odd. Now one more A, that is means even. So when the number of A's in XA was odd, you entered in state E and hence done. Next case is XA, XB is what you are going to process. And number of A's in X is odd. If the number of A's in X is odd, from the induction hypothesis, you know that the processing of A, X finished in O. Okay, after X, what you are going to process? It's a B. So after X, you are here and you are processing a B. So you are in O itself. And you are done because now the number of A's in XB is odd. Because number of A's in X was odd and now you processed a B. So odd number plus 0 is odd. So when the number of A's in XB is odd, you entered in state O and you are done. Okay, and next case is XA when the number of A's in X is even. The number of A's in X is even means the processing of X entered in E. And after that, what you are processing? You are processing A. So you are in E and you are processing an A. You are coming to O. Okay, in that case also you are done because now the number of A's in XA is odd. Okay, why? Because you know that the number of, from the assumption, the number of A's in X is even. Plus one more A means an odd number. When you processed a string of length k plus 1 where number of A's is odd, you entered in the state O and hence you are done. And the last step is what you are processing is XB such that the length of X is k and the number of A's in X is even. Number of A's in X is even by induction hypothesis implies you finish processing of X in the state E. So you are in E when you finished processing X. So after X you are processing a B. So where will you go from E? B is taking you back to E. So you are in E itself. So you are done. Why? Because number of A's in XA is even. Why? Because if the number of A's in X is even, you are processing one more. So there is a typo. This should be XB. Okay, XB is even. Why? Because an even number plus 0. This should be. You should read it as B. So you are ending in the state E. So you are done. So what I proved is that, and if I process a string of odd number of A's, I will finish in O. And if I process a string of even number of A's, I will finish in E, and that is the subclaim. And we have to prove that when X is a string of odd number of A's, then X is accepted by the language. Assume that a string X is containing odd number of A's. Then from the subclaim we know that the processing of A ends in O. O is a final state. So you entered in a final state and hence you accepted X and X is in the language. Okay, so with that we are finishing the completeness proof of this DFA design. So we have used mathematical induction to prove that the DFA design is both sound and complete, and which enables us to conclude that the design is correct. Okay.